Welcome to the Driving the World podcast series. I'm your host, Cully Holland. Today we have Don Congdon, a corporate trainer, and we're going to be discussing encoders. Hey, Don, thanks for coming back.
Yeah, nice to be back, Cully, and we're going to dive in and take a look at a topic I enjoy very much.
That's right. We're still talking about encoders, so this is our second episode. Hopefully, all of our listeners did listen to the first one before diving into this one. I think it laid a nice foundation for the conversation we're hopefully going to have here. So, we were talking about encoders and, like I said, covered some of the bases, but we didn't really talk about types of encoders. So,
Right.
are there like encoder classes or certain encoder types our customers should be aware of?
Yes, there are two broad categories of encoders, and this refers to really how they communicate their information to the VFD. They are incremental encoders and absolute encoders. Very broadly speaking, incremental encoders are primarily aimed at speed-based applications where you're trying to run the motor at a very specific speed. Absolute tend to be used for positioning applications where you're running the motor to produce a specific amount of movement. Now, that said, there are plenty of exceptions. You can use an incremental encoder for positioning in many cases, and you can use an absolute encoder in speed-based applications. So it's not hard and fast, but incremental encoders are cheaper than absolute, so we tend to see them more in speed-based, and absolute do have some advantages, which biases them toward positioning.
It is nice to have a general idea of which one's which or where you want to go to, even if there are exceptions. So today, let's kind of dive into the incremental encoders. Well, look, how and when should we use an incremental encoder a little more in depth than the broad two sections we just talked about?
Okay, yeah, let's talk a little bit about how incremental encoders work, and then I think you'll see why they're so good for speed-based applications. I don't know if you did this when you were a kid, but when I got my first bicycle, I made this fun discovery that if I took a stick and I stuck it in the fork so that it projected into the spokes, when you'd ride your bike, you'd get this neat clicky sound, and the faster you rode, the faster it clicked. Well, that's basically what an incremental encoder is. It's kind of like an optical bicycle wheel connected up to the motor shaft. And instead of using a stick, it uses a light beam that shines through a disc with little black lines on it. And what happens is, as that disc turns, the motor spins it. The black line interrupts the light beam, and it's translated into electrical pulses that come out. So you get these electronic clicks, and the faster the motor turns, the faster the encoder turns, the faster the clicks come. The VFD times the clicks, how far apart they are, and using that information, it figures out how fast the motor is turning. It's a really simple, elegant solution. A few details, though, we need to understand about incremental encoders. When you buy them, you have to decide what resolution you want. And the way resolution for incremental encoders is specified in what are called increments per revolution. Every time the incremental encoder clicks, that's an increment. And a typical incremental encoder might have 1,024 increments per revolution. So if you took that little disk out inside there, you'd see it has 1,024 tiny little lines inscribed on it. And that gives you an awful lot of clicks per revolution. And the reason you want that is the more clicks per revolution, the more accurately you can control speed. And of course, as you can guess, you pay more money for a higher resolution. So you decide how good a speed control you need, and that kind of determines what kind of encoder resolution you buy.
I mean, that's a great real world example that I think almost everybody can relate to. I know I used to playing card instead of a stick. I ruined a few cards, but that is a nice way to think of it and even understand the difference in the increments that you're getting. So we have an incremental encoder. Last podcast, we talked a little bit about cabling, communication, touched on it briefly. So once I get an incremental encoder, if I have an incremental encoder, is there only one way to communicate with it? Is it just cut and dry, or do we have some options?
Yes, incremental encoders, like all encoders, have an interface. That's the electrical set of specifications and connections between the encoder and the VFD. In our last podcast, I said you have to have a VFD that's encoder capable, and it's got to have an encoder interface that matches what your encoder has. Incremental encoders tend to have probably, I'd say, 3 or 4 different interfaces are the most common. The most common ones include what are called TTL, HTL, sine, cosine, and I'm also going to introduce a new one that SEW has produced within the last few years called MoviLink DDI. Let me tell you about these briefly. HTL and TTL are both practically the same thing. The only difference is the voltage that they use when they're communicating. These output little rectangular waves, what we call square waves. If you hook an oscilloscope up to an incremental encoder and you spin it, you'll see a square wave come out of it if it's TTL or HTL. This is a really simple communication standard, and a lot of the less expensive VFDs use TTL or HTL for their encoder interface, and it's a perfectly serviceable one, works just fine. But a really nice one that's much better is called sine cosine. And this is a very clever interface because it's actually got several outputs on it that the VFD combines together to get a higher performance. And what the VFD does, it uses these multiple signals to get more information out of that encoder. And what's really nifty about sine cosine encoders, if you buy one that's got 1,024 increments per revolution, the VFD turns it into 4,096 increments per revolution. So it quadruples the resolution.
Wow.
Using that technique, which is why sine cosine interfaces are very popular on incremental encoders because you get a lot from them. And then I'll mention the new kit on the block, MoviLink DDI. This is an SEW standard we've come up with. It's a single cable motor solution, uses just one hybrid cable for everything, and carries a digital data stream from the motor to the VFD, actually multiple digital data streams. And one of those can be from an incremental encoder. So the VFD just connects to this single cable. It communicates with the motor, it controls it, and it gets the encoder information. So those are your major interfaces.
So last podcast we talked about having a VFD that's capable of reading and working with an encoder. Sounds like we also need to make sure our interfaces are going to play nice going from the encoder type to the VFD as well, which is great to know. And it sounds like in the encoder world, we kind of mentioned tons of options. You kind of got to weave through it. It's a world of its own. But if we're talking about incremental encoders, does SEW have one, some options? How does SEW fit into the incremental encoder world?
All right, SEW offers a lot of choices. As always, we're a company with many choices,
Yes, we are.
sometimes more than I wish we really offered. But anyway, yes, let me tell you just briefly about encoders, how we identify them. We use a nomenclature, and by SEW standards, it's a relatively simple one. It only has 4 characters to it, and all our encoders work this way. The first is a letter that indicates the kind of encoder, and this is easy. All incremental encoders begin with the letter E. Then after that is a letter that indicates how it attaches to the shaft. An example of that might be a K, which means cone shaft. Remember, Germans use Ks a lot rather than Cs, so
Yes,
it's a
they do.
K. Another example would be S for spread shaft, or I for internal, which would be one of those built into the fan. So an EI8Z, for example, is a typical SEW encoder. This is an incremental encoder. It's internal. It's built into the fan. EI8 is just the series number. That's our current series, so you'll see a lot of 8s there. And then finally, the last character indicates the interface type, and Z means it's MoviLink DDI. We also sell an EI8C, which is the same thing but with an HTL interface. We sell an EI8R, which is a TTL version of that. So nomenclature is pretty simple. Just remember, identifies the type of encoder, the shaft attachment, the series, and the interface. I'll mention just one other, and this is an old favorite. It's been retired now, but there are a bazillion of them out there. It is the ES7S. This is an incremental encoder with a spread shaft attachment. It was from the previous Series 7, and S means sine cosine interface. So this was a very popular one. There's a lot of them out in the wild. You could run into one of those. So those are a few examples.
Well, it sounds like we utilize that nomenclature pretty well. Every character is needed, but also straightforward and not too confusing. I think we've covered incremental encoders pretty well. Is there anything you want to add before we wrap this one up? Or are we good to go?
I think we're good to go.
Well, fantastic. Thanks again, Don. I look forward to sitting down with our third episode on encoders.
All right, see you later.